Okay, so let's now see quickly how the variance relates with the mean squared error or the expected squared error. Okay, so the variance is over here. Okay. So note that so the only difference between these two quantities is that in the expected squared error you have the difference between the estimator, which is y, and the true value that you would like to estimate, while here you have the difference between the estimator and the expected value of that estimator. Okay. So this is why as I was saying, if y happens to be unbiased, okay, then the expected value of y is equal to p, right? And this basically means that so the variance is equal to the expected squared error or the mean squared error of the estimator y. Okay, so this is also denoted by MSE of y. Okay, so this is exactly the same. So what if y is biased? So if y has a non-zero bias, what we can do is you can still estimate, you can still compute this this quantity. So if I look at y minus p whole squared, you could write it as expected value of y minus the expected value of y plus expected value of y minus p whole squared. Okay, so I'm just adding and subtracting this term expected value of y, and now we can do this trick where you say that this is actually the expected value of, I'm using linearity of expectation. First I'm expanding this out and I'm using linearity of expectation, and I end up with something like y minus expected value of y whole squared plus this thing squared. Think of it as like a plus b whole squared, where a consists of these two terms and b consists of these two terms. Okay. So I have this plus a squared plus b squared, which is expected value of y minus p whole square plus 2ab, right? So that's 2 times y minus expected value of y times expected value of y minus p. Okay. Now what the linearity of expectation allows you to do is, I have the expected value of this large of the sum of three terms, okay, and it allows you to write it as the sum of expected values of the three terms. Okay. So this one can be written as expected value of y minus expected value of y whole square. So the first term, need not write it. So this is exactly equal to the variance, right? So this expectation is equal to the variance of y. Okay. And what is this term, right? So expected value of y is some fixed quantity, right? So it does not vary. It's actually the expected value. So it's some fixed value minus p whole square. So if you remember, this is exactly the definition of the bias, expected value minus the parameter of interest. Okay, and you have an extra square outside, so it is the bias of y squared. Okay. Plus you have this term which is 2 times the expected value of y minus expected value of y times expected value of y minus p. Okay. Now this is a constant. Okay. So what you can do, so I'm going to go over this a little bit fast because it's not terribly important, is that this is a constant, So expected value of something times a constant will just be 2 times that constant, which is expected value of y minus b, times the expected value of y minus e of y. Okay, now I don't need the extra parenthesis over here. Okay, what did I do here? So think of this as some random variable z. Think of this as some constant, let's say some 5 or some constant like that. Then I'm just saying that expected value of z times 5 is just 5 expected value of c. So it's simple. It's as simple as that. All I'm doing is this is some random variable. It has some expectation, and this is some constant because expected value of y is some constant. This in fact is exactly the bias, right? So this is some constant, and so this is what I'm using here. Okay, so this is if you have something like this, z times some constant, this would be 5 times the expected value of c, right? So that's all I am using there. Okay, so this is what we have. Now what you will note is that expected value of y minus expected value of y, so this term will be exactly 0. Okay. Then to see this, you again just simply have to use the linearity of expectation. Okay, so what this means is that overall, so this whole term becomes 0. Okay, so what you end up with is just variance of y plus bias of y squared. Okay, so that's exactly all you have. So the mean squared error of some estimate y, some estimator y, is basically the variance of y plus the bias of y squared. Okay, so this is a simple property that the mean squared error satisfies. Okay, so now let's get back to our example. Okay, so getting back to this example of a coin whose heads probability is 0.1, and of course you don't know this, and you are given a bunch of examples, right? And what we just defined is that if you had only 2 data points, 0, 1, and your y was deduced from that by taking the empirical average, then this estimator that we had, which is y being x1 plus x2 by 2, this is an unbiased estimator because its expected value is equal to p. Okay. And secondly, it had a typical squared error or the mean squared error which had some value. Okay, so let's now see what's how you would improve this estimator, right? So how do we improve this estimator? Okay, intuitively the previous estimator was bad because you had exactly 2 samples, right? So you just had some x1, x2. Okay, so intuitively more samples should help. Okay, and this is what we will see more formally now. Okay, and we will do this by looking at the mean squared error or the variance of these estimators. Okay, we will formalize this, the variance, and in this case also the MSE, because the estimator will turn out to be unbiased, drops as n increases. Okay, so this is what we will see today. Okay, so let's stick, so now suppose you have the same model as before. Let's stick to the same model. So xn, and these are all So this is a term I will use later. So these are all distributed as Bernoulli P. Okay, so this symbol just means these are distributed according to this distribution Bernoulli P. Okay, people also read this as these are drawn from Bernoulli P. Okay. All right, so you have x1, x2 up to xn like this, and let's consider the same estimator, which is y, which is x1 plus x2 to xn divided by n. Okay. So now I would like to show two things. Okay, so two main claims. Okay, first one is that for any n, y is an unbiased estimator. Okay, for p. And the second one is that MSE of y decays with n. Okay. In fact, the dependence will be proportional to 1 by n. Okay. So this is a symbol. This is not alpha. This means proportional. 1 by n. Okay, so these will be the two main claims, and let's see the proof of these two claims. Okay, so the first one turns out to be very easy. So let's see the proofs. So the first one, how do you show that an estimator is unbiased? So to show one, all we have to do is need to show that expected value of y is actually exactly equal to p. And how do you do this? You just use linearity of expectation, right? So y is equal to x1 plus x2 up to xn divided by n. Therefore, expected value of x1 plus x2 n divided by n, this is equal to 1 by n times the expected value of x1 plus expected value of x2 plus expected value of xn. Okay, because expected value of the sum is equal to the sum of the expectations, and you have a by n is a constant, so this is what you have. Okay, and so this is it, right? So now what is each for every I, right? Expected value of xi. So what is this quantity, right? So this one, xi is distributed as a Bernoulli, so it's 1 with probability p and 0 with probability 1 minus p. What does that mean? So it means that the expected value of xi is 1 times p plus 0 times 1 minus p, and this is exactly equal to p. So this is what we have. So each of these terms is equal to p. Okay, so this is equal to p, this is equal to p, and so on. Okay. So this overall expectation, this value, so this turns out to be equal to 1 by n times p summed n times, so this is np. So this is exactly equal to p. Okay, so we have shown that the expected value of y is exactly equal to p, which is what we needed to show for proving 1. Okay, so pause for a bit and look at the proof again if you would like to see this. Okay. So let's now go to the second claim, which is to analyze the mean squared error of y. Okay, so let's do that. So what is the mean squared error of y? So by definition, this is equal to the expected value of y minus p whole squared. What I'd like to point out is that all of these calculations are simply you use the definition of expectation, you use linearity of expectations, you use definitions of y and expand it out. Okay, you just have to be brave and expand out all these terms. Okay, so that's what we're going to do. Okay, so what is this? So this one is the expected value. Let's plug in y. Looks messy, but it doesn't matter. So it's x1 plus x2 plus xn divided by n minus p the whole squared. Okay. You will do a similar computation in your homework, so here's a heads up in homework 5. Okay, so this is what we have. Okay. So this is the expected value. I just plugged in what y, the definition of y. Okay, so you can now try to do this by saying, okay, so let me try to expand this out, and I can use the fact that this quantity is like y squared minus 2py plus p squared. Okay, and you can use linearity of expectation over there. Okay, so that's one way of doing it. Okay, so let me, and there's another way of doing, which is to view the p as n times p divided by n, and there's a sleeker way of doing it. Okay, but let me do this naive brute force way, because I just want to show that there's nothing very deep about these things. Okay, so you can always just expand them out and do it. Okay, so let's do it starting with this definition. Okay, so you have, this is the term that you have. Okay, so MSE of y is because of this expansion, so this you could also write it as expected value of y squared minus 2p expected value of y. Okay, because expected value of 2py, p is a constant, so that's just 2p times expected value of y, plus the expected value of p squared. P is a constant, expected value of a constant is that constant itself, so you get p squared. Okay, I'm just using the fact that if I have some expected value of some constant like 1/4, it's a constant, so it's always expected to be the same thing, so it's 1/4. So that's what you're using. So this is what we have. Okay, so, and I have already told you that this quantity is equal to p. Okay, so this is something we saw here. Expected value is equal to p. Okay, so this one is expected value of y squared minus p squared. Okay, so far so good. So where y is the sum of xi divided by n.